Because I think it should be a blip on that map.
Yeah, yeah. Well, what we're looking at here are the plates. Probably, I'm sure you've heard of plate tectonics. And believe it or not, I mean, I remember it was very controversial in the 80s. You know, I remember sitting in my grandparents' house and, you know, like, what the heck, really? The Earth is, you know, we're floating on crust, floating on magma, what? Well, that's how the mountains form, and et cetera, et cetera. So what we're looking at basically are healing or sealing cracks in the Earth. So if you go back and watch your Neil deGrasse Tyson and look at sort of the birth of the Earth, it was basically just a lot of rocks smashing into each other really hard. And, you know, as the poor thing was cooling, at some point it looks like a rogue planet came through, smashed into the Earth, and that's how the moon was formed. So not very hospitable for life. So we're sort of this, we're now on this nice, cooling ball of, you know, dirt, rock, a little bit of water and air sailing through space. But what we're seeing here are basically friction points or thinner regions in the Earth's crust. And so I think they're even showing here how the plates are moving. And the cool thing here, you can see this African plate is moving that away. The, what do they call this one? South American plate is moving that away. And, you know, thus, like, oh gosh, it looks like these two continents used to be attached, which they were. So, and what we're looking at in various places are where you have major high enthalpy geothermal energy producing areas. So let's talk about enthalpy a little bit. It's kind of a new word for us. Sounds a little like energy, sounds a little bit like entropy. I know there'll be some good questions about this on the exam. Yeah.
I was looking at Moodle and I saw our exam 6. Are we going to have a final exam too? Because I didn't see it on the syllabus.
I have a, gosh, it's weird. My pen works on one page, but not the other. Exam 5 is going to cover geothermal and wave power. Then exam 6 is pretty short. It's just on integration.
Okay.
Yeah. So
and that's all of it. We don't have
that's all of it. And there is a final.
Okay. Yeah.
But you know, you guys are doing well enough. You don't have to take it. I'll put it out there if you want to just take it for fun. There's kind of some neat engineering type problems on there. It's mostly quantitative. You know, I give you all week to take it. It's calculating things like, hey, if I've got a hydrogen aircraft, how long do the wings have to be so it floats? So, you know, it's some kind of simple Newtonian mechanics, just kind of gee whiz stuff mainly. Yeah.
The next exam, which I guess we're still covering
Yeah.
is on it, isn't open yet on Google.
Yeah, I'll open it Thursday.
Okay.
Yeah, so I'll open that Thursday. So you'll and it's relatively straightforward. It's gonna do the wave tech that we did last week, the geothermal we're doing now, and then we'll cover integration next week, and then we'll be done. Yeah, that's it. Yeah, yeah. Okay, so enthalpy. Enthalpy. That's defined in the book. Let's just go out and find a definition for it. So it's just remember last time we talked when we were looking at those. We were looking at the energy in a wave. We said you could have kinetic energy, potential energy, or internal energy. There are a few different ways to have internal energy. I mentioned a spring. Another one is heat. It's how much heat energy. So nice thing about it, not to be confused with entropy. So it's the internal energy. And there are a couple different ways, and a lot of times it's written with an H, but the nice thing about it, it has the same exact units as energy. So close this guy, it's not working. So enthalpy, typically H, the dimensions are equal to mass length squared over time squared. And it's measured in joules. So here's the main concept that I want to drive home here, is that if you have this is, it's particularly relevant for Montana. If you ever go out to Yellowstone or get in one of these hot springs, it's near a river. Let's see, let's do turquoise for this guy. So here's blue, here's cold over here. Let's get red going over here. Let's get red, pink, yeah, you can just do red and sort of scribble it in. So here's hot, there's cold. If you have hot on one side, cold on the other, you can basically build an engine. That's the whole point. So if we go back to these guys, these are places where you have enough temperature that you can make steam and spin a turbine and make electricity. That's basically what a high enthalpy geothermal site is. It's hot enough that you've got steam, and you can let that steam go to a colder state, and that's what actually does the work. So here's your hot side. Q is thermal energy flowing. Out comes the work, pushes the turbine, spins the magnet, makes the electricity, and then some energy is lost, it comes out colder, and then sort of dumps to the cold side. So that's the whole point of high enthalpy geothermal. Another system, low enthalpy geothermal. So this is high enthalpy. So here goes your Q, hot, Q, cold. Here's your engine, out comes your work. So this is high. Another one, I'll just draw a little sketch here. So a few years ago, my parents had the opportunity to build a house out on a lake. There were a couple little streams coming in. I was telling you about this. A couple little streams coming into this lake, and so they built a dam. And what they were able to do, and so they're pretty far. They're not off grid, but they're far enough out in the country that it was not practical or feasible to bring natural gas, and they also didn't want to have a propane tank sitting around either, so that it's just a 100% electric house. But to supplement the heating loads, what they did was put a little coil out in the lake. We were also talking earlier, the university does this too. The university has geothermal heating. And so what you do the lake temperature is relatively constant. And just for the sake of argument, I'm going to say it's close to cave temperature. 52 degrees is sort of average Earth temperature year round. So 52 degrees in the lake, and maybe dead of winter it's not going to be that warm, but there will be days where the air, and remember, the air changes temperature much more quickly than the ground or the water. So on a day, here comes a 32-degree blast. Well, where's my heat energy? It's sitting in the bottom of the pond.
Degrees Fahrenheit. Yes.
Degrees Fahrenheit, yep. Degrees Fahrenheit. Bottom of the pond, so you've got your pump. And of course, you've got your circulation system in the house, pump turns on, relatively cold air from the house, or cold energy, the Q, goes out, and back comes relatively warmer. And you can do think the same thing in the summer. Here comes a big hot day, it's 80 degrees, 90 degrees. Well, that 52-degree water is still sitting there. Again, turn on the pump, send it out, and it comes back. This is a low enthalpy. And basically what you're looking at is less than 100 degrees centigrade. So less than boiling, or less than any system, or less than 212 degrees Fahrenheit, right? So that's low. High, what we're looking at is greater than 100 C, or greater than 212 Fahrenheit. Because again, to make electricity, you've got to get to those boiling temperatures, make your steam, spin a turbine, etc. Yeah.
What's going on inside that circle?
This circle right here?
Yeah.
Well, inside this circle is a, it could be a combustion engine. So there's some machine is spinning. You could even look at it as your, it's not the best analogy because a wind turbine is not a heat engine, but you could think of this. So obviously there's more energy per unit volume. And here's another symbol I want to show you. If you do H sub V, this is, or sometimes it's just written as little h. That's the energy per volume. It's how much energy is in a liter of fluid, liter of rock, liter of air, what have you. It's the heat inside that. So this is it's a machine. It's some machine that's spinning and giving you work. So and that's pretty simple. But just think, engine.
So it's just a
Heat engine. Yep. And this is exactly, this little diagram is what made Sadi Carnot so famous back in the 1830s, 40s, where he's out there in France and watching these coal trains moving back and forth. It's like, okay, I was just born on this planet. What the heck are these coal trains? But he also realized that if France could make their engines more efficient, the train's going to go farther, right? On the same amount of fuel, you're going to go farther. Same thing. That's why, all of James Watt's work was so critical to the success of the British Empire, if you will. I mean, they how do you get your boat around the world with just a certain amount of fuel on board? Well, sit down, pencil, paper, make it more efficient. So that's what that is. Yeah. Yep. It's a machine. Yeah. Heat engine. Okay, so that's high enthalpy versus low enthalpy systems, because this very first figure introduces the word enthalpy. That's why I wanted to make sure we know what that is. Okay, so here's a couple plants, and you look at the towers there. Why do you need the towers? Well, it's the same way that just think of our own human bodies. When you want to go and work out, you have to get rid of the extra heat because your body wants to operate at its perfect temperature. Those cooling towers are basically this side right here. Where's the cold side? It's everywhere. It's just the average ambient temperature of the air. It's whatever you've got to work with. If the average temperature of the air goes up, your efficiency starts to go down. If it's nice and cold outside, your efficiency goes up. Iceland does a lot of
100%.
What's that?
They have 100%.
Iceland? Oh, you did a little research on Iceland, didn't you? Yeah.
I think them and Costa Rica and 2 other countries.
Yeah.
Have 4 countries in the world now last year ran on 100% renewable.
Yeah. The trip about Iceland, I think they've got so much excess electricity. It's very easy for them to import scrap aluminum. So whenever whenever they're running high on electricity, they can make aluminum there. The scrap.
The average person in Iceland, this was for the first paper we wrote.
Oh, yeah.
186 times the power that someone in Bangladesh.
I know.
186 times.
Well, yeah, it's interesting you mentioned that too. I just want to take a little side journey here, and this was something that fascinated me kind of back in the day. If you look at where our so here's north, here's south, here's the equator. If you look at where our species originated from, we did not. It wasn't up here. It wasn't down here. It was somewhere close to the equator, and it was a place on the planet that where you're in relative equilibrium with thermodynamics. Like, you don't need an air conditioner, you don't need a heater. It's just like you don't need those technologies. As you migrate further north, further south, the sort of the what's the word I'm looking for? The distance that you're traveling from thermodynamic equilibrium becomes greater. Just because your body temperature is much warmer than your surroundings, and so you need more house, more fuel, more everything. I think that's why you see that with Iceland. I don't know how much of it's actually utilized versus.
Well, I think they just have so much energy available to the average citizen that they just don't care.
Right.
And it's guilt-free energy too,
Right.
considering the way they run their
Right.
country.
Right. Yeah. Yeah.
Bangladesh can't even barely feed their people.
I know.
They're
Yeah.
right on the equator anyway, so no one's heating anything, no one's cooling.
Yeah. Right. Exactly. Yeah. Yeah. Yep. Yeah. All right. So those are some large geothermal, high enthalpy plants. Here's what's going on. Someone was mentioning, why don't we just go ahead and tap Yellowstone for its energy? Well, let's go. I'm ready. It's right there. But what we can see here again is sort of the results of the ancient Earth still there cooling, and it says crystallizing granite. Well, that's because it's molten granite, and as the Earth cools, more of that hot liquid core turns into colder, solid mantle. Here's your aquifer, impermeable rock or cap seal. This is why people are worried about the Berkeley Pit. And I don't know all of the geology there, but they're kind of in a place where if the water gets any higher, it sort of comes up into the aquifer, and then all that cadmium and lead and crap gets in your drinking water, etc. But if you are hot enough from all of the pressure, and so just basically look at this cap rock as mass times height times gravity. I mean, there is a lot of pressure. You wouldn't think of it. You wouldn't go out in your backyard and say, oh, there's a lot of pressure down here. But have somebody bury you in dirt at the beach, and all of a sudden, you can feel the weight of that sand forcing down. So the pressure and the force will basically is what squirts the steam out. What's kind of difficult for me to understand is, why doesn't this stuff just squirt out over here? Well, the whole system, it looks a little bit like the U-trap, on your toilet bowl, under your sink. You under your sink, what's that little guy? That's kind of what this is. It's kind of like a natural trap because there's just as much pressure here as there is over here. So the weight of the ocean, stream, aquifer, etc., pushes that down, and so you can sort of see a little bit of a cycle, right? And this is going back here, page up. I mean, this this guy right here is basically underground. That's the hot side. And this guy basically right here is the Earth's surface. So that's how to think about that. Right there is almost your heat engine. Right, the Earth is now sort of a heat engine. Out comes the steam, and now you've got your work. Then you put your technology in there to make your electricity.
Since we brought up Yellowstone,
Yeah.
One of my geology professors back at the University of Wyoming,
Yeah.
he was the guy that actually did all the geophysical mapping.
Oh,
of
cool.
the plume underneath.
Oh, yeah.
And yeah, he thought it would be interesting if humanity could find some sort of equilibrium with the world's hotspots where you're bleeding off enough of that pressure and turning it into energy to prevent catastrophic explosions.
Yeah, I like that idea a lot. And I know there's another team is now doing some more mapping down there. And yeah, I like that idea a lot. You tap it at a sustainable rate rather than waiting for the next big one, so to speak. Yeah. That sounds like a good engineering project to me.
It does.
Yeah, that sounds like a really good, fantastic engineering project.
You're killing two birds with one stone.
Yeah.
And if we don't avert that potential crisis, we're looking at catastrophe that could create another Marianas Trench, like separation of the continent sort of thing.
Well, yeah, I know, I don't know that much about it, but I know that the frequency with which Yellowstone goes off does tend to have a pretty catastrophic effect on, living systems, right?
About every 700,000 years.
700,000.
I think it's like 60,000 years overdue right now.
Yeah.
It's prime. There's plenty of energy down there.
Yeah.
Apparently the sun and the moon have a lot of effect on it.
Oh, this is true. Yeah, thanks for bringing that up. You don't think about it that much. We did tidal energy a couple of weeks ago, but the fact that the core is liquid, and the moon is constantly running around, sort of affecting those bulges. Yeah, it's a really good point. Really good point. Little invisible gravity waves yanking at the poor planet. Okay, so this guy, I think there's a couple things on Darcy's law. This is the last thing I'm going to do, and then we'll take a little bit of a break. But here's porosity in a system, and a couple terms. I think I've got a question or two on this. Is isotropic. And heterogeneous. So isotropic means a system that's the same in all directions. So iso is the same and tropic is move. An example of something that's anisotropic would be wood. If you look at wood. So the in a wood structure, if we just take a cross section, obviously it's going to be it's always easier to split the wood along this direction, right? Versus coming in with your axe. I mean, it's going to be much harder to penetrate that direction. And we also know that water flows preferentially this direction in wood versus radially. It flows axially rather than radially. So same deal in geosciences. So in this case, this thing is relatively isotropic because it's kind of the big things in each direction. So that you'd call this guy isotropic. You would also call it heterogeneous. This is relatively isotropic, but not heterogeneous because there's different sizes. This one, isotropic and heterogeneous, kind of the same in all directions. This one again is iso, but not hetero. Okay, and then this is showing This is showing a system that is not connected. So you've got, this is the type of stuff that you would want to build your life vest out of, because it's the water's not going to get inside the pores, so closed pores, versus this where it's open. And then finally, this is a great example of something that is anisotropic, because we can see that water in general would only flow in this direction and not that direction. And the thing that drives it, I know there's a little question on this, so it's Darcy's law. Let's just take a quick peek at Darcy's law, because that's what governs how water flows through different media.
Guess is it a man's last name?
I know. You kind of hope there's a famous woman out there named Darcy, but yeah.
Yeah, my mom really loved
Henry.
Pride.
Henry Darcy.
Yeah.
Pretty much guessed.
Yeah, I know. Well, just, this is not.
It's okay.
This is not very.
I'm not hurt by it.
Well, this is not very politically correct, but my doctoral advisor at the University of Michigan, we'd walk back and forth to the lab in her office, and there's Darcy, and there's Watt, and there's Jewel. She's like, oh, here we are along the Hall of Dead White Guys.
Yeah.
So, famous dead white guys. Well, there was a really cool quote about Curie, though. Marie Curie, not too long ago. She was quite the character. So what we're looking at in this system is the flow, and I apologize that they sort of ran out of letters, but Q is not heat in this particular instance. Q is the volumetric flow rate. It's how quickly something's flowing. So if we look, we can see that we have a, I don't know why they drew it this way. Oh, because it's negative. Okay. So there's a negative sign out here. If you look, the flow is going from left to right. So obviously the pressure to drive that flow is going to have to be greater over here.
It's a quadratic equation.
No, this is linear.
Oh, really?
Yeah, it's a linear equation. It's not quadratic. Nothing is squared
Oh,
in there.
yeah.
Nothing is squared in there. So the thing to keep in mind here is that you've got high pressure over here, low pressure over here. Low and high. This is going to be negative. Double negative is a positive, so that creates positive flow in this direction. You can see there's length, so it means that the longer the tube, the less flow. So when L goes up, Q goes down. When L goes up, Q goes down. And you see that, right, when you're in your garden hose? You get big old long garden hose, and yeah, it comes out lower because it's got farther to go. You have a pressure drop, basically. Area just means that the bigger it is, the more flow you have, right? If you want more flow, make the area bigger. This is the viscosity, so this is how sticky the water is. And for the hydraulic systems that we're talking about in geothermal, that's not going to change. What does change, this is the critical number right here, is that kappa. And that's just the permeability or the porosity. So if we go back here to our figures, this is going to have a relatively high kappa. These are all relatively high. You start looking here and it's relatively low. Now, one thing you mentioned there, Rob, and I'm going to just say this one last thing about it and I'll wrap up. In its proper form, this is actually a tensor equation. So it's linear, but it's written here as a scalar equation, just one dimension. But I'm guessing if we go down, yeah, it becomes a scalar. So pressure is a scalar, but this guy right here is the derivative of it. So in a system, you can always have it's a spatial derivative. So it's showing how the pressure is changing in different directions. So that it then becomes a vector, and so that delta or the del, it's just called DEL, del P, tells you in what direction the pressure is changing the most. In the systems that we were looking at before, obviously in the Earth, the pressure goes up as you go down. The lower you go, the higher the pressure goes. So the pressure gradient points down.
So more forces are about you.
Yeah. And so it gets kind of fun and crazy in a little bit. So this guy right here, that kappa Ni, says that you can have flows in three different directions. That's what that actually means. And obviously you can in any solid. So this is what's going on every time you squeeze a sponge. The water's looking for the path of least resistance, and that's what.
Sponge is isotropic.
A sponge would be most sponges are fairly isotropic. Yeah, I mean they're kind of the same, unless you had
So
like.
it's really about water flow and permeability?
Yeah.
That's kind of what it's about?
Yeah,
Okay.
yep, exactly what it is. Okay, we'll take a little break. Be right back.